Okay, let's go ahead and get started. So last class, we began our discussion of the motion of rigid bodies, which is the first example in this class of a mechanical system, which cannot be reduced to a system with one degree of freedom through judicious use of conserved quantities. And we started out by asking how one would compute the kinetic energy of a rotating object. So to compute the kinetic energy of a rotating object, we imagine that the object is rigid, so it is given either by a collection of point masses or a distribution of mass density, which is all fixed in position relative to one another. And the kinetic energy is 1/2 omega ij, omega j, summed. Jesus Christ. Okay, for some reason this eraser is not working. So I will just have to, there we go. Okay, the sum over I and j of 1/2 omega ij, omega j, where the omega i's are the components of the angular velocity vector in a coordinate system which is rotating along with the body. And Iij is the inertia tensor whose components are given by the following formula. So if we have a collection of masses labeled by an index alpha, then we sum over m alpha r alpha squared delta ij, the Kronecker delta symbol, minus r alpha I, r alpha j, the I and j indices of the position vector of one of the components, alpha of the system. So, and there was a similar formula that I wrote down last time, which allowed one to compute the inertia tensor of a rigid body which is made up of some mass distribution. So now, given this formula for the kinetic energy of a rotating object, we can now ask how one would describe the dynamics of some rigid body which is moving freely in space. So let's consider the dynamics of a free, which is to say not subject to any external forces, rigid body. So the first statement that one needs to understand in solving this problem is that the most general motion of a rigid body is a translation along with a rotation. So if we imagine that we start out with a rigid body with some fixed position and orientation, then the configuration space, the space of dynamical variables, will include the translations of this object along with possible rotations of this object. So if we let R alpha denote the position of, is there a mistake somewhere? The most general motion, sorry. Yeah, the motion is silent in this expression. Thank you. The most general motion of a rigid body is a translation plus a rotation. So that means that it will be convenient, if I wish to describe the dynamics of a rigid body, to do the following. So let's let R alpha denote the position of one of the parts of the system, one of the points that make up this rigid body. Then I will write this as the sum of two terms. So this, of course, this position will be some function of time. And what I'll do is I'll write it as a center of mass position plus some deviation from the center of mass position that I'll call delta R alpha, which will also be a function of time. So here, this is the deviation of a given part of the system from the center of mass. And so, what that means is that, by definition, because capital R denotes the position of the center of mass, the sum over alpha, m alpha, delta R alpha will be equal to 0. That is the definition of the center of mass. Okay. Yes, question? Yes. So the center of mass is defined so that our center of mass is defined by 1 over the sum over alpha m alpha times the sum on alpha m alpha times r alpha. So if you plug this in to the formula for r alpha and you sum over m alpha and divide the whole expression by the sum over m alpha, you'll see that the sum over alpha, m alpha, delta r alpha has to be equal to 0. That's the definition of the center of mass. So the utility of using the coordinates relative to the center of mass is that the sum of all these deltas is equal to 0. And you will see in a second exactly why it is that this is so useful. So now, in order to study the dynamics of this system, let's write down the Lagrangian. So because there are no external forces, the Lagrangian is equal to the kinetic energy, which is 1/2 the sum over alpha m alpha r alpha dot squared, which, if we plug in our expression for r alpha, is the sum of three terms. So we have 1/2 the sum on alpha, m alpha times r dot squared, from this term right here, plus a term which is the sum on alpha, m alpha, r dot delta r alpha, plus a term which is the sum on alpha, m alpha, delta r alpha squared. And so is that clear? All I've done is plug in this expression for r alpha into the formula for the kinetic energy. I'm sorry, and 1/2. Thank you. And the point is that because I have chosen a center of mass coordinate, this expression here is r dotted with the sum on alpha, m alpha, delta r alpha, which is equal to 0. So we see that the Lagrangian is the sum of two terms. It is 1/2 times the total mass, which is the sum on alpha, m alpha, times the center of mass position squared, plus the kinetic energy of the rigid body expressed in terms of a rotation about the center of mass. And that, according to our discussion yesterday, is 1/2 omega ij times the sum over I and j, omega ij, omega j, where ij is the inertia tensor, evaluated about the center of mass. So if you remember at the beginning of class yesterday, we asked what the kinetic energy of a rotating object was. And so we computed this expression up here, and we showed that it could be written in terms of something quadratic in the angular velocities, whose coefficients were this inertia tensor ij. So this is really the utility of the center of mass coordinate, because we see that the center of mass motion is exactly that of a free particle with position given by the center of mass position and mass given by the total mass. And the rotational factor completely factors out. So we have a sum of two separate pieces. So the center of mass motion of a rigid body can be treated exactly like that of a free particle, with some mass, capital M, and position, capital R. And all that remains to do now is to study the dynamics of the rotating piece involving the angular velocities and the inertia tensor. So because of this, we can just focus on the rotation term. Yes, which involves the inertia tensor. That's correct. This is the rotation term here. So T rotation, which is 1/2 sum over ij, omega I ij, omega j. Any questions? Okay. So what we now need to do is compute the equations of motion coming from this rotation term. Now, there are two different ways of proceeding in computing these equations of motion. We could treat the delta R alphas as dynamical variables on which the omega i's depend, and write out the Euler-Lagrange equations explicitly treating these delta R alphas as our degrees of freedom. That is the straightforward way of proceeding. However, it's in fact much easier to make the following observation. So let's notice the following. This action is rotation invariant. So this system is rotationally invariant, which means that the equations of motion will imply that angular momentum is conserved. So if we wanted to, we don't even have to write out the equations of motion to know that these equations of motion will imply angular momentum conservation. And in fact, a very slick and easy way of getting the equations of motion is simply to write down the statement that angular momentum is conserved. So let's go ahead and do that. Is everyone clear why this works? I mean, this is a little trick. If you like, I encourage you to go ahead and compute the Euler-Lagrange equations explicitly. It is, I'm sure, an instructive exercise. But let's be lazy here. It's always good to be lazy. And use angular momentum conservation to write down the equations of motion without ever doing any actual work.
Just a quick question.
Yes.
So you said you want to focus on the rotational term. Why only on the rotational term?
Because we've already solved for the center of mass motion. The center of mass motion is just that of a free particle. So it moves on a straight line. Okay. So let's compute the angular momentum. So the angular momentum is given by the following formula. So the angular momentum is just the sum of the angular momenta for all of the different parts of the system. So if we have a rigid body, which is made up of a bunch of parts labeled by an index alpha, then we sum over alpha the angular momentum vector for each of the individual parts, which is m alpha, r alpha cross r alpha dot. It's the sum of r cross p, m r cross v. Now, what is r alpha dot? I suppose I should have written delta r alpha and delta r alpha dot there. For convenience, I will just leave off the deltas and remember that we're working in a coordinate system where the center of mass is at the origin. So what is r alpha dot? Well, this is what we did yesterday. R alpha dot is omega cross r alpha, because the system is undergoing some rotation parameterized by the angular velocity vector omega. So the angular momentum is the sum over alpha, m alpha, r alpha cross omega cross r. Is that clear? Any questions on that? So now I would like to appeal to a formula that you may or may not remember from vector calculus and rewrite this term as the sum over alpha, m alpha, times the sum of two terms. So perhaps you remember from vector calculus the following formula: A cross B cross C is equal to the sum of two terms. I forget what those two terms are, but we can always figure them out. I think it's B times A dot C minus C times A dot B. Right. Is that right? I think that's right. We know that it has to be right because the expression, so we can use the same logic that we used last time in remembering this expression. It has to be linear in A, B, and C. And it has to be perpendicular to A because it's A cross something. So it has to be a linear combination of B and C. And it has to vanish when B and C point in the same direction. And you can see that if B and C both pointed in the same direction, then the linear combination that I have written down vanishes. And so the only thing that's left is to determine the overall sign, which I think I've gotten right here. Have I gotten it right? You were nodding. I've gotten it right. So, yes, I've gotten it right. That you just have to remember the right hand rule. This is my left hand, so I won't get it right. But you have to remember the right hand rule in order to get it right. Okay, so let's use that expression. So that's r alpha squared times omega minus omega dot r alpha times r alpha. So what I would now like to do is note that this, in fact, is a rather familiar object. So let's remember that the inertia tensor was the 3x3 matrix whose components were given by the sum over alpha, m alpha, r alpha squared, delta ij, minus r alpha I r alpha j. And the angular velocity vector was the vector whose components were omega I. So if you compare this expression to these two formulas, and you imagine writing the angular momentum in our rotating reference frame, its components will be given by Li, Ei, and those components, so let's compare this expression here to this expression here. You see that this expression in the angular momentum is just this matrix I acting on the vector omega. So L is I times omega. Omega is a vector, I is a matrix, and you can see, well, what happens if you act this delta ij on omega. Delta ij is the identity matrix, so that just gives you omega. And if you take this guy and you use your usual rules for matrix multiplication, you'll get the vector r times r dot omega, which is this term up here. So the angular momentum vector is the inertia tensor times the angular velocity. In the same way that the linear momentum is the mass times the linear velocity. Remember I told you yesterday that the inertia tensor plays the same role for rigid bodies that mass plays for particles undergoing linear motion. And so just as the linear momentum is the mass times the linear velocity, the angular momentum is the inertia tensor times the angular velocity. So Li is the sum over j, ij, omega j. Is that clear? Are there any questions on that? I encourage you to go and write out the matrix multiplication explicitly if this is not clear. You know, write out Iij as a 3 by 3 matrix and multiply it times the three component vector, which is the angular velocity, and check that you get precisely the angular momentum vector. Okay. Well, now that we know that the angular velocity, the angular momentum is just the inertia matrix times the angular velocity, it's really easy to write down the equations of motion. Because the conservation of angular momentum is just the statement that L dot is equal to 0. So let's go ahead and compute L dot. So L vector dot is the time derivative of the sum over I. Sorry, there was a sum over I here. I always forget my sum over I's. At this point, you're probably used to putting them in by yourselves. It's the sum over I, Li, Ei, which is the sum of two terms. So there's a first term, which comes from taking the time derivative of the components of the angular momentum vector, computed in the rotating reference frame, times Ei, plus a second term, which comes from computing the time derivative of the basis elements of this rotating reference frame. So that's Li times omega cross Ei. Now we can just go ahead and plug in our expression for Li. So this expression is the sum over I times Li plus omega cross, so plus Li dot plus Li times omega cross Ei, which has to vanish. And so if we go ahead and plug in our expression for Li, well, Li dot is the sum on j, Ij, omega j dot. Yes?
So you're taking Li dot, dot I, and then here in the other part you're taking cross. So you're factoring, but one of them is a dot product and the other is cross product.
There are only cross products. There's only Ei. What's that?
And I dot Ei.
Li is a set of three numbers which are the components of the angular velocity vector in this rotating coordinate system. And there's no dot product anywhere. Yes. So it's just as our discussion of rotating reference frames. Is that clear? I'm not sure.
Okay, yeah. So in the second line, you go Li omega cross,
and
then you close the parentheses.
Yes. So that is Li times, so that's a vector here. Yeah, these are vectors. And Li is not a vector. It's just a set of three numbers. So There's a vector. So yes, there's no dot product anywhere here in this expression. There's Li. This is a set of vector expression, which is the same as this expression. All I've done is pull out an overall bracket. Is that clear? Any questions so far? Okay, watch carefully. Nothing up my sleeves. So, what is Li dot? What if I want to compute the time derivative of the components of the angular momentum vector in the rotating reference frame? Well, I made a big deal last class of the fact that the inertia tensor is constant in time. So when we compute its time derivative, the only place that the time derivative appears is in the time derivative of the angular velocity. So if I wish to write out this expression a little more explicitly, it is the sum over j, ij, omega j dot. And then I have to decompose the Li omega cross Ei in terms of the Ei basis. So omega cross Ei is the sum over j epsilon ijk omega j ek. Sum over k there too. So this expression is the sum over j iij omega j dot plus epsilon ijk times the sum over k ikl times omega l. And all that is equal to 0. Is that clear? So let me write this a little more cleanly. The sum over j iij omega j dot plus the sum over j and k epsilon ijk. Oh, I'm sorry, I missed an omega there. Right, there was one omega coming from here and another coming from there. So there was an omega j. Omega j ikl. Oh, I'm sorry. I meant... Yeah, there's a sum over L here, too. Omega L. Sorry, is that clear? Did I put in too many sums all at once there? Yeah. That's equal to 0. So let's go through that a little more carefully. So omega cross E is the sum over J and K, epsilon ijk, omega J ek. Omega J is, okay. Then, yeah, I also flipped my indices around a little bit. Okay. So let's write this out a little more explicitly. So let's write this out a little more explicitly. Okay. So what is this term here? So here, yeah, okay. So we're working out Li omega cross Ei, which is equal to the sum over J and K, Li epsilon ijk omega j ek. And then we're using the fact that Li itself is the sum over L omega, so I L omega L. And putting that all together gives me this expression here. So this expression that I've written down is a little complicated. It's not that complicated, but it's a little complicated. And so it's We never actually end up using this form of the equations of motion for a rotating rigid body. Instead, it's much easier to use the expression in principal coordinates, where ij is, yes?
Sorry, should you add sum over I for the truth equation when it's equal to 0? Because you added sum over I before.
Yes, I was only looking at the EI component of that in writing this.
You're saying so each EI component must
Yes.
be equal to 0.
Each EI component must be equal to 0. That's correct. Sorry, is this derivation still unclear? Okay. Okay, well, how about this? Let me tell you one more thing, and then I'll rederive it for you in a completely different way, which will make it which will make it much more clear. Okay. So in principal coordinates, the inertia tensor, the inertia matrix, is diagonal. So that means that it's equal to I. So remember, I sub I was one of the principal moments of inertia. If I is equal to j, and it's 0 if I is not equal to j. So so if we wanted to, we could of course use principal coordinates, in which case L, the angular momentum vector, the component of the angular momentum vector is just I times omega I. There's no sum on I here. Is that clear? So the angular momentum vector was the inertia matrix times the angular velocity vector. And if the inertia matrix is diagonal, then the components of the angular velocity vector are just I times omega I. So L1 is I1 times omega 1, L2 is I2 times omega 2, so on and so forth. So then, that makes life much easier. So the statement that L dot is equal to 0 is the statement that Li dot plus epsilon ij k omega j L k is equal to 0, summed over j and k. That's just using the fact that EI dot is equal to omega cross E. And then plugging in this expression, we have Li. So Li dot is I omega I dot plus the sum over j and k, epsilon I j k omega j I k omega k. And that all has to be equal to 0. So this derivation has the advantage that because I'm using the principal axes, I have a lot less sums floating around. But you can see that if you took this expression, so my claim is that if you took this expression, where I did not work using principal axes, and you set the inertia tensor to be diagonal, then you would just get this expression. So is this derivation a bit clearer, hopefully? Okay. I heard someone say yes. Okay. Would you like me to go through this again? Okay. So, I understand. I sympathize that I'm throwing sums around and epsilon symbols around all over the place, and it does take a little while to get used to. But in fact, the strategy is really quite simple. The components of the angular momentum vector are the inertia tensor times the angular velocity. The inertia tensor is constant, so when I compute the time derivative of the angular momentum vector, and I set it equal to 0, I get the sum of two terms, one of which involves the time derivative of the angular velocity, and the other of which comes from the fact that the coordinate axes in a rotating coordinate system themselves depend on time. So I have that same stupid E dot term that's been bugging me for the last 2 weeks. And that leads to this epsilon symbol because I have a cross product, because E dot is omega cross E. So I encourage you, this is one of those derivations that you only really understand if you go through it yourself. So tonight, as you're lulling yourselves to sleep, I encourage you to try and go through this derivation if what I have said today is not 110% clear. So this is the equation of motion for a rigid body in the rotating coordinate system using the principal axes. Now, there are 3 such equations, because I have not summed over I here, I remind you. So there's one equation for each value of I. So I could write these out a little more explicitly. So there's I1 omega 1 plus this complicated epsilon symbol business. So I is equal to 1 here, and so epsilon 1 jk is non-zero only when j and k are equal to 2 and 3, or 3 and 2, respectively. So this is the sum of 2 terms, omega 2, omega 3, times I3 minus I2 is equal to 0. And likewise, the equation when I is equal to 2 is I2 omega 2 dot plus omega 1 omega 3. And now we just need to look at the signs here. So I is equal to 2, so j and k will be equal to 1 and 3, respectively, with a plus sign when j is equal to 1, and a minus sign when k is equal to 1. And finally, the third equation says omega 3 dot is proportional to omega 1 times omega 2 times the difference of I2 and I1. So these are the 3 equations of motion for a rotating rigid body, and they are known as Euler's equations. So, are there any questions on this derivation? I am highly sympathetic to the fact that I have freely manipulated indices and gone through the summations relatively quickly. So it's probably good if I paused here and asked if there are any questions. Hopefully, at the very least, the basic strategy and the basic idea is clear. Yes.
So these equations will help us to find the omega dot or to solve for omega dot?
Yes. So the goal, of course, is to solve for omega. So the goal at the end of the day is to solve for the position of the body as a function of time. So the goal is to solve for the rotation matrix, describing this rotation as a function of time. In order to do that, we want to solve for the angular velocity as a function of time. Because, as you showed on your last problem set, the rotation matrix is found by taking the time-ordered exponential of the angular velocity matrix. And so we need to compute the angular velocity as a function of time. And here we now have the set of 3 differential equations which one must solve in order to compute the angular velocity as a function of time. So our goal is then to compute omega 1, omega 2, and omega 3 as a function of time by solving these equations. And these equations are really not so bad because the i's are just constants because the moments of inertia don't depend on time. So this is just a set of 3 relatively innocuous-looking differential equations for the angular velocities. So before proceeding to discuss the solutions to these equations of motion, I should probably mention one comment here, which is that these equations of motion describe the rotation of a free body, which is not subject to any external forces. But if the rigid body is subject to an external force, then rather than solving the equation L dot is equal to 0, the angular momentum will no longer be conserved. And so the derivative of the angular momentum vector is then set equal to whatever torque is applied to the system. So, for example, I believe that in one of the problem sets due next week, you will have to consider an example where an external torque is applied and study the subsequent motion of a rotating rigid body. But first, let's just consider the case where I have no external torque. Any questions on that? Yes.
In the differential equation, when we have the torque, the right-hand side will be different than 0.
Precisely. So the right-hand side, when we have torque, will be non-zero. But before proceeding to consider problems where you have some complicated torque, as you will for your next problem set, let's just consider the case where we have a free rotating body. Now, these three differential equations, they really look rather simple. The i's are constant, and we just have three first-order differential equations for the omegas. So, you have been taught throughout your careers as physicists that when you encounter a differential equation, it's, all you do is you look it up in some book and write down the solution to the equation of motion. And this is a simple enough looking differential equation that if there were any justice in the world, you would just be able to go and look in some textbook and write down the solution to this differential equation. But despite what your parents may have told you, there is no justice in this world. And in fact, it is impossible to find explicit, simple analytic solutions to these equations of motion. I think this is an important life lesson. It's an important life lesson here, which is that when you're considering something like the Kepler problem or an oscillator or a 1D system, then generally you can always find reasonably explicit exact solutions, either through simple analytic functions or by performing an integral, which you may or may not be able to perform explicitly, but at least you can understand. Here, however, this is our first example of a system which quintessentially has more than one degree of freedom. And so even though these equations of motion look rather simple, they are nonlinear, they are coupled to one another, and so there simply do not exist simple analytic expressions for the answers. So our goal over the rest of this class will not be to write down an analytic expression for the solution to these differential equations, although, not terribly explicit, but analytic expressions can be studied. Instead, what we will try and do is study them in certain regimes where we can understand intuitively what is going on. So let's just consider a variety of special cases. Yes? Do you have a question? Okay, sure. Sorry about that. Okay. Sorry about that. So let's try and solve Euler's equations. So let's first consider the following simple case. So let's consider the simplest possible object, which is one whose moments of inertia are all equal. So let's consider the case where I1, I2, and I3 are all equal. So this would correspond to an object with complete rotational symmetry. So this would be a spherically symmetric object. such as a spherical shell or a solid ball or something like that. So in that case, these equations are very simple. I1, I2, and I3 are all equal, so I3 minus I2, I1 minus I3, I2 minus I1 all vanish. So these equations of motion just say that omega 1, omega 2, and omega 3 are constant. So in the rotating coordinate system that we are using, a sphere or a spherically symmetric object will just spin about its axis with constant angular velocity. Okay, well that was pretty easy. Let's proceed to the next simplest case. Let's consider the case where I1 is equal to I2, but not equal to I3. So Tuesday when we were working out examples of inertia tensors, we encountered a variety of objects for which this was the case. And all of these objects had some rotational symmetry. So indeed, examples of objects with two equal moments of inertia include those which are axially symmetric. So for this reason, an object which has two equal moments of inertia is usually called a symmetric top. So, for example, you can imagine an object which is formed as a object of revolution around some symmetry axis. So, I don't know, we have some blob. Okay, that's not a very symmetric looking blob. We have some symmetric blob, and then we form the blob of revolution by revolving around some symmetry axis. I'm sorry, that's not a very good picture. Let me try and draw a very good picture. Okay, we have some symmetry axis, and we have, say, I don't know, a sort of turnip-looking shape there, for example, where we form this shape by revolving around some axis of symmetry. Then here, the z direction, or the 3 direction, will point along the axis of symmetry, and the I1 and I2 principal moments of inertia are the moments of inertia along the plane transverse to the axis of symmetry. Okay, so let me just remind you what Euler's equations were. So I1 omega 1 dot was equal to omega 2 omega 3 times I2 minus I3, which is the same as I1 minus I3. Likewise, I2 omega 2 dot was equal to omega 1 omega 3 times I3 minus I1. And I3 omega 3 dot was equal to omega 1 omega 2 times I1 minus I2, which is equal to 0. So the first thing that we see is that because we have two moments of inertia equal, omega 3 is a constant. So the angular momentum in the direction of, the angular velocity in the direction of the axis of symmetry is constant. Yes?
On the first equation, the I1 minus I3 should be I2 minus I3.
Yes. I1 is equal to I2. Indeed, if I wanted to, could write this as I1 here. Yes. Yes, so I'm using the fact that I1 is equal to I2. Okay? Now, because omega 3 is equal to constant, we're in business. So let's just, and that's because the remaining two equations are now linear equations for omega 1 and omega 2. let's go through this. So let me define capital omega to be omega 3 times I1 minus I3 over I1. Then the remaining two equations are omega 1 dot is equal to capital omega times omega 2, and omega 2 dot is equal to minus capital omega times omega 1. Even I can solve these differential equations. So one way of solving this differential equation is to take the time derivative of the first equation and insert the second equation, and you see that omega 1 double dot is equal to minus omega squared omega 1, which is the equation for a simple harmonic oscillator. Those damn simple harmonic oscillators just keep showing up all over the place. And likewise, the equation of motion for omega 2 will also be that for a simple harmonic oscillator with frequency capital omega. So the solution then will be that omega 1, omega 2 is a constant, which is the amplitude of the solution of the simple harmonic oscillator, that I'll call omega naught, times some sum of sines and cosines. So I will just choose the phase of my oscillation so that omega 1 is sine omega t. I could, of course, choose it to be cosine omega t. I could choose it to be sine omega t plus cosine omega t. I'll just choose my phase so that it's sine omega t. And then omega 2 can be computed by calculating omega 2 dot is minus capital omega omega 1, which, if you work it out, implies that omega 2 is cosine omega t. So what we see is that, at least in the case of a symmetric top, it's possible, and indeed relatively easy, to completely solve the equations of motion. So what does this mean? So are there any questions on this solution? Yes?
Is omega naught related to omega 3?
No, omega naught is a constant of integration, right? When you solve the equation of motion for a simple harmonic oscillator, the amplitude of the oscillation is a constant of integration. So that's what this omega naught term is. There's another constant of integration, which is the phase. So in principle, I could put, instead of t here, I could put t minus t naught. I've just set that equal to 0 for I've set t naught equal to 0 for simplicity. Do you want to put it in? Let's put it in. Live dangerously. That's what I say. Oops. Boy, that's too dangerous. So sine omega t minus t naught, cosine omega t minus t naught. What's that?
On what you decide for omega 1 you took only the sine, and for omega 2 you took the
Yeah.
cosine.
So of course, by choosing t naught judiciously, I could change that sine into a cosine and vice versa. If I set t naught to be, what is it, pi over 2 omega, right? That's what the effect of this t naught term is, to the same as that of doing. If you remember our discussion of the simple harmonic oscillator, we saw that rather than taking a linear combination of sines and cosines, we could also include that in a phase term t naught. So yes. Any other questions? So what does this mean physically? What this means physically is that, unlike the case where we had spherical symmetry, the omega i's are not constant in time. Omega 3, the angular velocity in the symmetry direction, will be constant, but the angular velocities in the directions perpendicular to the axis of symmetry will not be constant, and in fact they'll rotate. So the direction of spin is not constant, but rather precesses around the axis of symmetry. And the frequency of this precession is capital omega, which I remind you was given by the ratio I1 minus I3 over I1 times the angular velocity in the direction of the axis of symmetry. And what's really sort of interesting is that the sign of capital omega depends on whether I1 is larger than I3 or not. So that means that the direction of precession depends on whether I1 is bigger than I3 or I1 is less than I3. So, for example, if you have an object which is short and fat, so that I1 is less than I3, then capital omega is negative. So if you look how the angular velocity evolves, well, its component in the z direction, in the 3 direction, will be constant, but it will rotate around in what I suppose from a top-down point of view would be a clockwise manner. So if you took Danny DeVito and you spun him, he would precess around his axis of symmetry in the approximation that Danny DeVito is completely symmetric in a clockwise manner. However, if you took Robert Brandenberger, excuse me, if you took an object that is tall and skinny, maybe not Robert Brandenberger, if you took, yeah, oh, yeah, they were in a movie together. No, Arnold Schwarzenegger is roughly spherically symmetric. If we took Robert Brandenberger and the approximation that Robert Brandenberger is actually symmetric, then he would precess in a counterclockwise direction. I don't know. I should come up with a different example of someone who's tall and skinny. Barack Obama, he's tall and skinny. Okay. Now, I should point out that this precession of a symmetric top is of more interest than simply the behavior of Danny DeVito if he's spun. For example, another object which is rotating and which is approximately actually symmetric is the Earth. So, of course, the Earth is not spherically symmetric, but rather has a slight bulge at the equator. This can, of course, be understood from our study of non-inertial reference frames, where we saw that due to the centrifugal force, the effective mass of an object at the Earth's surface was reduced by, I believe, around 0.3% at the equator relative to the North Pole or South Pole, which means that effectively the Earth will bulge slightly at the equator, much like Danny DeVito. So it turns out that I1 minus I3 over I1 of the Earth has a magnitude of around 300, So it's a dimensionless number, which is about 300. So, and of course, omega 3 is around 1 inverse day. So we expect the Earth should precess with a period of around 1 over 300 inverse days. And indeed, this has been observed. It is known as the Chandler wobble. Its amplitude is absolutely tiny. Sorry, the frequency is 1 over 300 inverse days. The period is, sorry, with a frequency of 1 over 300 inverse days. So a period of around 300 days, around a year. Sorry, is that what you guys were whispering about? Good.
Seems short.
It's about a year. Yeah. So, in fact, it turns out that, I'm working under the approximation here that the Earth is both axially symmetric and completely rigid. The Earth, as you may know, is not completely rigid. The oceans, for example, are highly non-rigid, being liquid. And even the Earth's crust is not completely rigid. It has some flexibility. So, in fact, experimentally, this has been observed with a frequency of 1 over around 435 inverse days. So we're off by 30-40% here. And the observed amplitude is actually absolutely tiny. It's only around a 10-meter displacement from the North Pole. So the axis of rotation, which you would have thought was exactly the North Pole, in fact precesses around the North Pole with an amplitude of around 10 meters and a frequency of a period of slightly longer than a year. Okay. Any questions on that? Yes.
Sorry, should I say 1 over 300 on the top?
Yes. Thank you. Sorry about that. Yeah, of course you're right, because omega is I1 minus I3 over I1. Yes. Thank you. Sorry about that. Good. Any other questions? Okay. So we've now exhausted all of the easy cases. So let's consider the most generic situation. So let's consider the most generic sort of rigid body, where I1, I2, and I3 are all distinct. So now, as I said, there's no explicit analytic solution to the equations of motion. So in your problem set due next week, I've outlined a set of steps where you can go through and understand intuitively what the motion looks like, at least in a certain approximation. And what I would now like to do is provide another set of alternate intuitive reasoning for you to understand the generic motion of a rigid body. So the basic idea is the following. So even though we don't know how to find the general solution, there are certain particular solutions which are easy to find. For example, let's ask whether it's possible to have a rotation which is just about one of the principal axes, say the I1 principal axis. So the equations of motion say that I1 omega 1 dot plus omega 2 omega 3 I3 minus I2 is equal to 0. I2 omega 2 dot plus omega 1 omega 3 I3 minus I1 is equal to 0. And I3 omega 3 dot plus omega 1 omega 2 times I2 minus I1. Is that right? Or is I1 minus I2? Let's see. Yes, it's I2 minus I1 equals 0. Did I get that right? Did someone look it up? Oh, is there a minus sign here? Thank you. Yeah. You just look at the first one and you do cyclic permutation of the indices. Good. Thank you. Oops, did I not change it? Okay. This will be important. Let's make sure we get the right signs here. So we have I2 omega 2 dot plus omega 3 I1 minus I3. Good. Did I get these all right now? Yeah. See, the nice thing about teaching a class is I don't have to get the signs right. You have to get the signs right, because you're the ones who are taking the class. I already got the signs right once long ago when I took this class, and once is enough. Okay. So let's look for a solution where all of where the object is rotating about one of the principal axes. So let's say omega 1 is equal to a constant, and omega 2 and omega 3 vanish. So you can see that if omega 2 and omega 3 vanish, the last two equations are automatically satisfied. So omega 2 and omega 3 vanishing implies that the last two equations automatically vanish, and omega 1 being a constant says that the first equation also works out. So this is indeed a solution to the equations of motion. Yes?
If you're saying that omega 2 and omega 3 are 0, so the last two equations become omega 2 dot is 0, then if you integrate, you'll get constant.
Omega 2 equals 0 implies omega 2 dot equals 0. So I'm not looking for a generic solution to the equation. I'm just looking for a particular solution. So what we've seen is that one solution to the equations of motion for an arbitrary rigid body is a rotation about one of the principal axes. Let us now ask whether this solution is stable. So you now know very well how we go about addressing this question. We start by asking what happens if we add a small perturbation to the solution. So let's imagine perturbing the system slightly by adding a small amount eta 1 to omega 1, as well as a small amount eta 2 and eta 3 to omega 2 and omega 3. So and then let's look at these Euler equations expanded only to linear order in the small perturbation, just as we did when we were studying an arbitrary one-dimensional system. So that first equation says that I1 times eta 1 dot plus omega 1 omega 2 I3 minus I2 is equal to 0. But omega 2 times omega 3 is quadratic in the small perturbation. So if we're only looking at the linearized equations of motion, then that first equation of motion says that eta 1 dot is equal to 0. Let's now look at the second equations of motion. So the second equation of motion says that I2 omega eta 2 dot is equal to the product of omega 1 times omega 3, which to linearized order is just capital omega times eta 1 times I3 minus I1. And likewise, I3, omega eta 3, right? Because there was an omega, the omega came from omega 1, and the eta 3 came from little omega 3. So I3, eta 3 dot, is big omega times eta 2 times I1 minus I2. So that first equation is easy enough. It just says that eta 1 is a constant. And now we can look at those second two equations. Those, we now are experts at solving that sort of equation. Eta 1 dot is a constant times eta 2 dot is a constant times eta 3. Eta 3 dot is a constant times eta 2. So if we take the derivative of this second equation and plug in that third equation, we will get the equation of motion of a harmonic oscillator. In particular, I2, eta 2 double dot, is equal to omega squared over I3 times I3 minus I1 times I1 minus I2 times eta 3. Eta 2, sorry, thank you. And if I wanted to, I could move this I2 to the other side. Now, here's the important point. This quantity that I have written here on the right-hand side of this equation will be positive or negative depending on the relative sizes of I1 and I2. So, the solution where the top rotates about the I1 axis will be stable or unstable depending on the sign of I3 minus I1 times I1 minus I2. If I3 minus I1 times I1 minus I2 is negative, then eta 2 double dot is something negative times eta 2, and that's the equation of motion for a simple harmonic oscillator with real frequency. If I1 minus I3 times I1 minus, if I3 minus I1 times I1 minus I2 is positive, then this is the equation of motion for a harmonic oscillator with imaginary frequency, whose solutions grow exponentially in time. Just like that for an unstable equilibrium, rather than a stable equilibrium. So the solution will be stable if this quantity is negative, and unstable if this quantity is positive. And so let's stare at this quantity here. So this quantity is negative if I1 is less than I2 and I3, or I1 is greater than I2 and I3. Whereas it'll be positive and the motion will be unstable if I1 lies between I2 and I3. So what does that mean? That means that if you look at an arbitrary object, it has 3 principal axes and 3 moments of inertia. And this object can rotate in a stable manner about one of the principal axes only if it is the largest moment of inertia or the smallest moment of inertia. The intermediate one will be unstable. Yeah, give it a try back there. Don't hurt anyone. So, a rigid body will rotate in a stable manner only about the principal axes with the smallest or largest moments of inertia. So on your problem set, I have outlined a completely different way of understanding this, which I hope you enjoy working through. And if you do not believe this fact, I recommend you find a book that you don't care very much about, or a tennis racket that is not particularly expensive, and you try and you throw it around enough that you can figure out exactly under which circumstances it will rotate in a stable versus an unstable manner. If you've ever played tennis, you probably already know in your head that there are two axes about which the tennis racket will rotate in a stable manner, and one axis about which it is very difficult to get the tennis racket to rotate. Okay, are there any questions? Oops, something happened here. Yes.
Would it help if we take the system of the two differential equations and solve for omega 3 as a function of omega 2 and omega 3 as a function of omega 1? Or
Okay, sorry, hang on. My computer's... Jesus fucking Christ. Recorded for all posterity. That's fine. Okay, now it's working? Okay. The eraser's not working. I swear I'm going to throw this fucking thing. Yeah, maybe the next thing I'll do is I'll check which axis this thing rotates around in an unstable manner. Okay, well, it looks like I won't be able to erase. Oh, now I can't even write. I can write on one side but not the other. Okay. Anyway, was there a question? Yes. What was the question?
So if we take the system of differential equations and solve for omega 3 as a function of omega 2 and omega 3 as a function of omega 1,
yes.
Would it help in any way, or it's useless?
Well, it does not particularly help. You know, you can try and... The problem is that it's a nonlinear differential equation. Unless one of these omegas is constant, the equation is nonlinear, and... you know, as you may remember from your differential equations classes, linear equations are, by and large, completely solvable. You can more or less figure whatever you want out about a linear equation. But nonlinear equations are, you know, in your problem set last week, you found the arbitrary solution of a linear differential equation formulated in terms of matrices. For nonlinear differential equations, life is just not so simple. And... there are certain examples where one can solve it explicitly, but in general, you're just out of luck. So, yeah. I encourage you to try and find an explicit solution to these equations, and you'll quickly discover just how difficult it is.
For example, the third order would work? The third order differential equation?
Well, I mean, you know, there are three first-order differential equations, so you can try and formulate them as a single third-order differential equation, but it's going to be very nonlinear. So, you know, that's not, it doesn't buy you very much. Okay, so this completes our discussion of the motion of rigid bodies. There's one final topic that I did want to discuss in the theory of rigid bodies. Let's see, I'm just about out of time. So maybe what I'll do is I'll defer that till next class. I wanted to discuss the theory of Euler angles, which really, it's only a 5-minute discussion. But I'll save it for next time. Okay. Any other questions before we conclude? Yes.
I don't think you can, but is there any way to have a rotation that's stable around an axis which is not a personal axis?
I believe it is. Let's see. The answer is no, and I invite you to try and prove that. I think the answer is no. Yes, the answer is no. I've already proven it. So I invite you to try and prove it. Set them all. Okay, here's a trick. Yeah. Okay. Now I'll let you prove it yourself. Yeah. Any other questions? Okay. I should maybe just mention there's one final topic that I did want to discuss in the theory of rigid bodies, which is that of Euler angles. Do you guys have 5 minutes now? Would you mind if I went on for? Someone said no back there. Okay, we'll just end now, and so we'll have to spend 5 minutes on rigid bodies, or should we just do it now? Is there anyone else who has to go immediately? Okay, I'll let you guys go. We'll do it. It's the end. It's Thursday. Okay. Next time we'll have a brief interlude on Euler angles before considering the general motion of n-body systems.